Hello everyone and welcome to this incredible channel. In today's video, I'm going to show you a way to get the mass conservation equation. Let's begin with the divergence theorem. Let omega included in R3 be a smooth domain. We have the integral of dv on the domain is equal to the integral of the scalar product of v and n on the boundary of our domain with n a neutral unit normal vector. What is interesting for us is the application to the mass conservation law. We consider a fluid in omega including in R3 moving with the speed v in x at time t positive with a natural density of the fluid so that we can compute the mass contained in omega, which is m omega at t equal integral of rho on omega. Omega is a fixed domain with respect to time of R3. Let's compute the mass variation in omega using two methods. First, the m omega at t over dg equals, by definition, the limit when delta t goes to 0 of omega at t plus delta t minus m omega at t divided by delta t, which is replacing with the definition of m omega the following limit. We can insert in the integral using the dominated convergence theorem, for instance. So we're finally the derivative of m omega t with respect to time equal to the integral of an omega of the partial derivative of rho with respect to time. Secondly, we can now compute the quantity of matter entering or leaving omega through its boundary. If V is parallel to the boundary locally, the fluid follows the boundary without crossing it, like on the area circled in red on the illustration on the right. If the normal component of velocity is positive, then, that is to say v scalar n positive, then the fluid will take delta t equal to L over v scalar n to leave the domain. It is the simple formula time equal distance over velocity with L, the distance between x and the boundary. Now, if v scalar n is positive, then the following quantity will exit the domain between g and 2 plus delta t. The integral on the element of the boundary such that v scalar n is positive of v scalar n times delta t times rho. On the illustration on your right, you can see there's locally some fluid leaving the domain through the boundary between t and 2 plus delta t. We can sum these quantities to get our integral. Besides, the larger the dot product of v and n, and the larger delta t and rho r, the more fluid exits the domain. If v scalar n is negative, then it will enter minus the integral of the x and the boundary such that v scalar n is negative. We have the same integral than before. Why is it there a minus before our integral? Because we need the integral to be positive, and it's also convenient to have a positive quantity of fluid entering the domain. So, in algebraic magnitude, it leaves from omega the integral on the boundary of v scalar n times delta t times rho, which is equal to minus m omega at t plus delta t minus m omega at t between parentheses. Here, we put a minus because if we look at the quantity of matter leaving here, then m omega at t plus delta t is strictly inferior to m omega at t, we want to work with positive quantities, because it would be odd to have a negative quantity of matter leaving or turning the domain. When you think about it, our integral can be considered as the opposite of the quantity of matter that is entering omega plus the part that is leaving already. So double minus for the integral related to the x on the boundary, such that the scalar n is negative. We end up having the same integral, and the sum of the two integrals gives us an integral on all the boundary. Besides, we have the same result, but the minus will appear on the left side term. So, before the integral, if we consider what's entering in algebraic magnitude. So, we then divide by delta g, which is that the derivative of m omega is equal to minus our integral, equal to minus the integral of the divergence of rho v on omega. For the second equality, we just applied the divergence theorem. We record that the first method gave us that the derivative of m omega is equal to the integral of the partial derivative of rho with respect to time. Thus, we can group all of this, where is equivalent to the random frame equality, gathering everything in one integral. We end up with the mass conservation equation because it is true for all omega in the domain. We prove this by reasoning by contradiction. Suppose f not identically equals to 0, let omega minus the set of x in omega such that f of x is strictly negative, and omega plus the set such that f of x is strictly positive. Then if the integral of f on omega plus equals 0, it implies f is 0 in omega plus. Same thing goes on omega minus. So we have f identically 0 on omega, because omega is the sum of omega minus plus omega plus, and when f is equal to 0, it's equal to 0. So f is equal to 0 in all omega, and it is absurd. We have our contradiction. So that's the end of the video. Thanks for watching. If you have any question, you are free to ask them, and it would be very kind to subscribe. Thanks for watching.